You saw the title. NASA claims a supersonic jet that lands a gentle sonic thump, not a boom. But how do you turn Mach 1.4 shockwaves into something under 75 PLDB on the ground? We'll dissect the hardware that does it. We'll map the long razor nose that spreads shock fronts, the top-mounted F414 GE100 that cleans up the belly, and the 4KE external vision system that replaces a canopy to keep the airflow tidy. By the end, you'll know which pieces matter, why they're placed where they are, and how they add up to quiet. Before we move on, please take a moment to subscribe to the channel and like the video. Everyone knows shockwaves stack into that harsh N wave, so the instinct says a longer body should just pile on more shock. Yet the X-59 stretches to 99 feet 9 inches, with a nose that takes nearly 1/3 of that length to do the opposite. It delays and staggers the pressure jumps so the ground hears a softened rise, not a single crack. The acoustic requirement is explicit. Keep the perceived level below 75 PLDB on the ground, and you only get there if the shock system never coalesces. The design objective is shaping, not muffling. Shocks form at every volume change: nose, canopy, inlets, wing roots, gear bays, tail surfaces, and in conventional layouts they merge and focus as they convect down to the ground. The X-59 aims to deny that coalescence, forcing each small pressure step to stay separate in time, which weakens the peak when it finally arrives at the observer. That runs against the grain of classic supersonic jets. Delta and ogive-nosed aircraft generate a strong bow shock and a strong tail shock, and the intermediate features tend to reinforce rather than cancel. Focus happens in caustic lines when the pressure field reflects off the ground. A longer, sharper forebody helps acoustically, but introduces two practical penalties. The pilot's forward view disappears behind a needle nose, and structural weight can creep because slender shells need stiffness. So the logic becomes rigorous. Area ruling manages cross-sectional slope so that the rate of volume change along the length is smooth and predictable. Chine geometry at the forebody guides the initial compression and controls where the first shocks shed, which buys time before the next set forms. If you spread volume additions, canard, cockpit volume, wing glove, so that each change is modest and spaced, you create a stair-step of microshocks instead of one cliff. Think of it like replacing a single loud clap with a row of finger taps. The total impulse is similar, but because each tap lands at a slightly different moment, the peak is much lower, and the ear interprets it as less objectionable. The X-59 applies that directly in metal and composite. Specifics matter. The forebody occupies roughly 0.33 of the total length, which gives room to shape the pressure rise before the wing contributes. Cross-sectional slope is kept low early, then allowed to grow gradually so the flow expects the next event. The canard sits forward enough to carry load and to generate its own mild shock early in the sequence, and the wing planform follows to avoid stacking at the mid-body. By this point, the pressure train is already spread out. Underside cleanliness is part of the same logic. Discontinuities on the belly produce secondary shocks that bounce and couple with the ground reflection, which then steepens the waveform. A smooth lower surface keeps the down-looking rays consistent, and that consistency prevents the classic reinforcement that produces the hard N. By way of example, Concorde created distinct bow and tail shocks that reach the ground as a classic N wave, with sharp onset and release. The X-59 instead seeks a shaped signature, the pressure trace rising and falling on a rounded slope, with peaks trimmed by the spacing of events and the avoidance of strong aft shock formation. When it works, the payoff is concrete. The elongated razor forebody with disciplined volume distribution prevents shock stacking, and what reaches the neighborhood is a softer, time-stretched pressure rise that meets the sub-75 PLDB target rather than a crisp boom. That forebody only holds the line if the rest of the airframe doesn't corrupt the field, which means the engine, the inlets, and the absence of a forward canopy have to cooperate. That forebody only holds if the rest of the airframe doesn't inject stray shocks, which is why the headline move is blunt. Put the F414 GE100 on top, and delete the forward canopy. The question isn't aesthetics. It's what the ground hears when the inlet lip, canopy bow, and gear doors are no longer feeding energy into the down-looking pressure field. The X-59 treats its underside like an acoustic instrument panel that must stay blank. The integration problem is basic physics and messy plumbing. Every break in curvature, engine inlets, cockpit bubbles, landing gear bays, sheds compression and expansion waves that couple as they convect and reflect. In conventional layouts, the belly is crowded, and those features form a ladder of shocks that steepen into an N-wave by the time they reach the observer. The X-59 instead makes the lower surface as smooth as a glider's, so the only major events are the ones intentionally placed along the long nose and through the canard wing sequence. That choice creates immediate trade-offs. A top-mounted engine sees local flow with stronger upwash and potential swirl, so inlet distortion margins become a first-order concern. Maintenance access can get worse, and the nacelle's weight sits high, which nudges stability and structural design. Remove the forward canopy, and you remove the pilot's natural horizon. If either decision fails in practice, the quiet boom theory collapses into operational compromise. So the propulsion installation is engineered to serve the signature. A single F414GE100 sits on the aft fuselage, with inlets shielded from line of sight to the ground. That geometry blocks direct inlet lip shocks from radiating downward and reduces interaction between the jet plume, the aft body, and the ground reflection. The aft position also keeps the highest pressure disturbances behind the carefully shaped forebody, so the early pressure steps aren't overwritten by a late, strong event. Forward, the E-external vision system replaces the canopy bulge with silicon. High-resolution cameras feed a 4K display, giving the pilot a stable forward view without adding a canopy bow that would otherwise reinforce the initial bow wave. This is not an aesthetic delete. It preserves the needle forebody's smooth pressure rise. With no canopy break in curvature, the first compression stays mild, and the timing spacing built by the long nose remains intact. Risk is managed by reusing proven subsystems. F-16 derived landing gear handle loads without a bespoke development cycle. T-38 cockpit elements, including the seat and an F-15 sourced life support system, reduce novelty in critical systems. One way or another, the team keeps invention focused where it matters: the aeroacoustics and the new vision and inlet integration. Flight test reflects that discipline. The first sortie at Plant 42 remained subsonic and short, enough to validate handling qualities, air data, telemetry, and the XVS under real lighting and glare. Then the jet moved to NASA Armstrong to open the envelope. Supersonic acoustic runs and community overflights follow, because the target condition is Mach 1.4 near 55,000 feet, where the shaped signature can be measured repeatedly over representative neighborhoods. There are counterpoints that don't vanish with shaping. Engine noise and emissions will still factor in commercial viability, and the F414's core acoustics on takeoff are not the problem being solved here. The regulatory question on the table is Overland acceptability of the supersonic signature, and this layout directly aims at that single metric. So the mini payoff is tangible. The top-mounted F414 cleans the belly's shock environment. The XVS removes canopy-induced disturbances. Legacy gear and cockpit hardware keep risk constrained. Together they preserve a shaped, low-amplitude pressure trace instead of an N-wave. And with those systems cooperating, the program can now gather the data set that actually moves policy. Measured, repeatable, community-verified quiet thumps. Quiet supersonic flight is a layout problem, not a gadget. The long forebody shapes the initial pressure field, the top-mounted engine avoids corrupting it from below, and the cockpit looks through silicon so the airflow stays clean. It was therefore designed to produce a thump, not a boom. So, watch the acoustic validation and the community response runs. Those numbers, repeatable PLDB measurements and tolerance surveys, will decide whether regulators adjust Overland rules. If you want the deeper dive on XVS crew workload and inlet distortion margins as they stretch to about Mach 1.4, say so below. The margins and procedures deserve their own treatment.
Signal strike.